Vesper numbers. The second digit of the Vesper number is the total number of bonds around the central atom. This means the number of single, double, or triple bonds. Remember, double and triple bonds only count as one domain. So, we did the first number before. Now let's look at the second number, which is just the number of bonds. For boron trifluoride, this is easy. Each of the bonds are single bonds, so each of the three bonds involved in the bonding domain are also single bonds, and so the second number would be 3. Now, in the case of xenon tetrafluoride, 6, because there were 4 bonds and 2 unbonded pairs of electrons to give the first number of 6. But now for the second number, we only want to count the bonds, which would be 1, 2, 3, 4. And that means that the second number would be 4. Now, let's take a look at ozone. So, of the 3 electron domains around oxygen, only 2 contain bonds. Therefore, the answer for the second number would be 2. The third digit of the Vesper number is the total number of lone pairs around the central atom. You can check your work. The first digit is always equal to the sum of the second and third. So, first let's do the third Vesper number for each of the 3 examples that we've been using. And then let's assign a Vesper number and a shape based on the Vesper number. So first let's look at boron trifluoride. There are 3 bonds around the central atom of boron, but no unbonded pairs, lone pairs. Therefore, the number is 0, and the total number is 330. For xenon tetrafluoride, as you remember, there are 4 bonds around the xenon, but there are 2 unbonded pairs right here, so therefore the third number is 2. And notice, 4 bonds plus 2 lone pairs, 4 bonds being the second Vesper number, 2 unpaired being the third Vesper number, 2 plus 4 adds up to the total number in the electron domain of 6. Finally, back to our friend ozone. Ozone has 1 lone pair to go with a 2 bonded pair, sets of bonds in the electron domain geometries. So therefore, 3 equals the 2 bonds plus the 1 lone pair. Now, let's go up to the chart. For boron trifluoride, it is 330. Therefore, this is trigonal planar. Second, this is 642. 642 is called square planar. And it's as simple as that. You simply assign the number, you then go to this guide and see what the shape is. 321, that is bent. And if you try and teach without Vesper numbers, you've got to look at the shapes and look at central atoms, things like that, and figure out the shape. But this way, if you can assign the Vesper number, which is really a very straightforward process, you then use this chart and you can assign the shape very easily. Now, when I taught this in first year chemistry, I let the students have this table of shapes. Unfortunately, when they're going to have to know this for the AP chemistry test, they will not have this table of Vesper numbers when they take the test. Therefore, with my students in AP chemistry, I will not allow them to have this table when they take a test, and unfortunately, they're going to have to memorize it. Linear molecular geometry. There is only one molecular geometry for 2 atoms or lone pairs around a central atom, linear molecular geometry, 220, with a bond angle of 180 degrees. This makes perfect sense as 2 points define a straight line with an angle of 180 degrees. This is the simplest molecular geometry. For molecules with 3 atoms around a central atom or with a Vesper number of first number of 3, these are called trigonal planar geometries. There are 2 forms of molecules in this case. Trigonal planar, if all of the electron domains have bonds, or bent, where one of the domains is a non-bonded pair. Let's take a look at each of these. And again, it's extremely helpful for all of these to have a model kit and actually look at the models while you're doing this. So, trigonal planar, right here, 1, 2, 3 atoms bonded to the one central atom. In each case, the angle is 120 degrees. Now, in the case of bent, you have the one unbonded pair. That unbonded pair pushes slightly down on the two pairs containing bonds, therefore transforms this angle from 120 to 117, and that these angles up here will be slightly greater than 120. Again, unbonded pairs of electrons repel more strongly than bonded electrons, thereby slightly shrinking the bond angle between the atoms. Typically, for the AP test, you do not have to memorize things like the 117. That really the only angles you really need to know are the basic shapes, the ones that have the 0 at the end of their Vesper numbers. Tetrahedral molecular geometry. There are 3 molecular geometries for 4 atoms and or lone pairs around a central atom. Again, with a Vesper number that starts with 4. Tetrahedral, if all are bonding pairs. Trigonal pyramidal, if one is a non-bonding pair. And bent, if there are 2 non-bonding pairs. Tetrahedral is 440, trigonal pyramidal is 431, and bent is 422. So let's look first at tetrahedral. This is the base shape, as is anything that with a Vesper number ending in 0. There are 4 atoms connected to the central atom with no bonding, unbonded pairs. Therefore, this angle is 109.5 for all of the different variations. For each of the angles is 109.5, which makes sense from Vesper theory, which says that the electrons will repel in order to put them as far apart from the other electrons as possible. It turns out that an angle of 109.5 will make this work. Now, let's look at trigonal pyramidal, 431. You have the one set of unbonded electrons. Those, as we saw in the 321, will push down on the other, pressing the bonded pairs slightly down so that they will have an angle of 107. Finally, bent 422 has 2 unbonded pairs. Those push even harder on the other bonded pairs of electrons, forcing that angle to 104.5. This is a fairly common angle. You might want to remember that as well, because this is water, and the angle is 104.5, and there may be reason to remember that. Now, when your Vesper number starts with 5 or 6, that means you have an expanded octet around the central atom. In the case of Vesper numbers starting with 5, they will all be a trigonal bipyramidal molecular geometry. Now, these molecules aren't that common, but they do exist, and your students are responsible for them on the AP test. The 4 shapes are, first of all, the 550 shape, the base shape where you've got 5 atoms located around the central atom. Notice that one of the pairs aligns in a straight line with an angle of 180 degrees. And then the other 3 atoms go around the middle, separated equally at angles of 120 degrees. Now, the remaining shapes. Seesaw is 541. These angles will be slightly different, but you will not be responsible for knowing the angles. T-shape, 2 unbonded pairs, and then linear, 3 unbonded pairs, just leaving the 2 atoms that are lined up. Again, especially with the 5s and 6s from the first Vesper number, it is extremely useful while you're teaching to have traditional ball and stick molecular models to use so the students can actually see that, for instance, seesaw looks like a seesaw when you turn it sideways from the way it's pictured here, and T-shape, as you see here, looks exactly like a T. These names may sound funny, but they're very descriptive, so it's good if your students can see them. The final set of molecular geometry you need to know is called octahedral. Octahedral is when you have a Vesper number that starts with 6. There are only 3 molecular geometries for 6 atoms and/or lone pairs around the central atom that we need to worry about. The first of these is octahedral, where you can see 6 atoms surrounding the central atom with no unbonded pairs. Remove one of those atoms and replace it with an unbonded pair, and you get square pyramidal. If you notice, it has a square base with one sticking off, making a square pyramidal shape. Finally, remove 2 of the unbonded pairs. You'll remove the 2 that have the 180-degree angle, and you'll be left with 4 arranged in a square. That's why this is called square planar. Again, draw the diagrams, figure out the Vesper numbers, and then they look like this. And again, also, molecular models will be very useful in helping your students understand these shapes. All right, let's practice drawing some Lewis structures and determining the electron domain geometry and the molecular geometry. Let's start with nitrogen trifluoride, NF3. Okay, first we must count the electrons. Sometimes I get lazy about this. Nitrogen has 5, and fluorine has 7, and there are 3 of them. That means we need to have 26 electrons. So let's take nitrogen, bond it to 3 fluorines, put the electrons around so that we get to 8. 6, 12, 18, 20, 22, 24, 26. This is the proper Lewis structure for nitrogen trifluoride. Now, let's find the Vesper number. How many electron domains are there around nitrogen trifluoride? Well, you have 1, 2, 3 bonds. 1 unbonded pair makes for an electron domain geometry of 4, or your first Vesper number is 4. Now, out of those 4, 1, 2, 3 are bonds, and the 4th is unbonded. So, this would be 4, 3, 1. If we look at our chart, that would be trigonal planar. No, it would not be trigonal planar. I fooled you. It will be trigonal pyramidal. The difference between trigonal planar and trigonal pyramidal is the 1 unbonded pair around the nitrogen. Now, the molecular geometry is determined by the first Vesper number, 4. So this is the molecular geometry. The molecular geometry is the whole number. The electron domain geometry is just the first number, 4, which stands for tetrahedral. All Vesper numbers starting with 4 will have an electron domain geometry of tetrahedral. The variations for molecular geometry would be 440, tetrahedral, 431, trigonal pyramidal, or 422, bent. All right, let's try another one. Let's do it for iodine pentafluoride, IF5. Now, let's immediately, when you see that there are 5 connected to the central atom, you need to think immediately about an expanded octet and something that is going to be more than 4 for a first Vesper number. In this case, it will undoubtedly be 5 or 6, because we know we need at least 5 around the central atom, and it may be 6, and let's see about that. Iodine has 7 valence electrons. Fluorine also has 7, and there are 5 fluorines. Therefore, the total number of electrons in this molecule should be 42. So, we'll draw it, F, and it doesn't matter at what angle you draw the F's attached to the I. You need 5 of them. You then need to put electrons around each of the fluorines. Iodine already has 5 bonds, so it is already past 8 and is up to 10 around the iodine atom. So we don't need to add any electrons there. Okay, each of the fluorines has 6 around it. So 6 has 5 times 6 is 30. 1, 2, 3, 4, 5 bonds around the iodine. Each bond counts for 2. That's 10. That equals 40. We need to get to 42. All we have is 40. The only way we can add electrons is if we put a pair of unbonded electrons around the central atom. We add those 2, and we get 42. So this is the proper structure for iodine pentafluoride. Now, Vesper number. How many electron domains are there around the iodine? I'll tell you what, let's use a different color so as not to be confusing. So let's get out green. So, unbonded pair, or bonded pairs, we have 1, 2, 3, 4, 5. 5 bonds around the iodine in the central atom. Let's get another color to look for this. We got red, and then we have the 1 unbonded pair around iodine. That's the 6th. So the EDG equals 6, the first Vesper number, equals octahedral. And I may have misspelled that, sorry. Now, the molecular geometry equals 6, 5, 1. 5 bonds around the iodine, and a 6th unbonded pair. So the 5 is for the bonded pairs, the 1 is for the unbonded pair. And if we look at the chart, 6, 5, 1 is square pyramidal. And see, I've been doing this so long that I basically have the shapes memorized. But it will take you a while to practice of doing that. So they're the answers. And just to confirm, we've done this for a while, so let's take a look. EDG is octahedral. Yes, I did misspell it. And the molecular geometry is square pyramidal. And it all comes right there from the Vesper number. Let's do another one. Let's do the nitrite ion, NO2 minus. Nitrogen, there are 5 valence electrons, 2 oxygens, each with 6, plus 1 for the negative charge, equals 18 electrons. So we'll put the N in the middle. It is the less electronegative of the 2. Put our O's on the sides, draw our electrons to get to 8. Let's count them. 6 around each oxygen is 12. 4 around the nitrogen is 4. And the 2 bonds is also 4, adding up to 20, which means that we're going to have resonance here. So that what we're going to have is, to do this, we need to erase those 2 and those 2 and take the 4 electrons and replace it with a double bond that will count for both nitrogen and oxygen. Now, this is resonance. Technically, to do it correctly, you would have to do this, this, a double bond without drawing the unpaired electrons. You're going to get something that looks like this, and technically to do this exactly right, we have to put brackets around the whole thing and a negative charge. But for doing this process, you don't need all of that. Now, how many bonding domains are there around each nitrogen? We have 1 bond, 2 bonds, remember double bonds only count as 1, and then we have the unshared pair, which is 3. So the first Vesper number would be 3. The EDG for 3 is trigonal planar. Now, of the 3, 2 are bonded and 1 is not. This is a molecular geometry of bent. Again, 2 here, 1, 2 are the bonded pairs, and then the third electron is unbonded, making for 3, 2, 1.